Functional groups are a tool that organic chemists use to classify molecules. This is something that's really important for you to learn, and more specifically to memorize. In order to really be able to do well in organic chemistry, you have to be able to look at a molecule and immediately be able to identify which functional groups are present. So let's start with the definition of a functional group. A functional group is a combination of atoms that, when present, are responsible for the physical and chemical properties of a molecule. So if we want to know how a molecule is going to react, it's very important for us to know what functional groups are present in it. Furthermore, functional groups allow us to classify molecules into families. Biologists like to classify organisms into kingdom, phylum, class, order, family, genus, and species. Functional groups also allow us to classify molecules. We could take a molecule and say that it is an alcohol, and then more specifically a tertiary alcohol, as we will see in a couple of moments. We will start our tour of the functional groups actually with molecules that do not contain any functional groups at all. These molecules are called alkanes. When I say they contain no functional groups, what that means is that they just contain the elements carbon and hydrogen, and all of the bonds are single bonds. Alkanes can be further subclassified into three categories. They could be thought of as linear, branched, or cyclic. A linear alkane simply has the carbons bound to one another in a straight chain. A branched alkane has, as the diagram shows, branches in the chain, so you might have groups going one way or the other way. And a cyclic alkane is when the carbons form a ring. At this point, we want to develop the relationship between the number of carbons and the number of hydrogens in an alkane. So in a simple alkane, if there are n carbons, there are going to be 2n plus 2 hydrogens. Okay, so for hexane over here, on the left, we can see that there are 6 carbons, and if you put the proper number of hydrogens on each carbon to give each carbon 4 bonds, you will end up with there being 14 hydrogens. 6 times 2 is 12, add 2 to that, and you get 14. When you have a ring, the rule is that each ring reduces the number of hydrogens by 2. So our structure on the right is a 5-membered ring. If there were no ring, there would be 12 hydrogens, but because there's a ring, we're going to reduce it by 2, and we will have 10 hydrogens to go with the 5 carbons. Alkenes are molecules that contain carbon-carbon double bonds. Okay, so in a simple example of an alkene is this molecule drawn here, known as 1-hexene. Alkenes are going to have formula CnH2n. Okay, so 1-hexene, instead of being C6H14, it's C6H12 if the molecule is acyclic and has only one double bond. In general, each double bond present in a molecule reduces the number of hydrogens by 2. Another more specific class of alkenes that we're going to look at a lot in the course of our exploration of organic molecules are known as aromatic rings. Aromatics, for the purposes of our discussion this semester, contain a 6-membered ring with alternating single and double bonds. This definition will be broadened in the second semester when we have an entire unit where we discuss what it means for a molecule to really be aromatic. And we're going to look at some examples that don't just have 6-membered rings and don't just have carbon and hydrogen. But that's coming up in the second semester. Finally, alkynes are molecules that contain a carbon-carbon triple bond. Okay, so here we have an example of a molecule that has both an aromatic ring and an alkyne. Moving away from molecules that contain just carbon and hydrogen, we get into the alkyl halides. Okay, so an alkyl halide is a molecule in which one of the hydrogens is replaced by a halogen. And you can do this very easily because both hydrogens and halogens can form one bond. A primary alkyl halide is one in which the carbon bound to the halogen is bound to one other non-hydrogen atom, thus primary meaning one. As a shortcut, you could look at this and say, okay, the carbon with the halogen has two hydrogens on it. And that is a shortcut that will work and help you be able to recognize primary alkyl halides. But the reason they are defined as being primary is because there is just one other non-hydrogen atom. This general scheme continues. Secondary alkyl halides are when the carbon bound to the halogen contains two other non-hydrogen atoms. Similarly, there is going to be just one hydrogen in this molecule on the carbon bound to the halogen. Finally, a tertiary is when the carbon bound to the halogen is bound to three other non-hydrogen atoms, and there are no hydrogens on this carbon. At this point, I want to introduce a new piece of terminology to you, and that is the R group. We use the letter R as an abbreviation for a generic organic or alkyl group when we don't care exactly what it is. Okay, so in this case, in the primary alkyl halide, we had an isobutyl group. In the secondary, we had two methyls. In the tertiary, we had three methyls. Well, all primaries, secondaries, and tertiaries are going to behave the same, whether they're methyl, ethyl, propyl, or what have you. So we're sometimes going to use this R notation in this case just to say that there are three organic groups there. We don't really care what they are, but the fact that they are not hydrogens, that they're organic groups, is what makes the alkyl halide tertiary. Moving on in our tour of the functional groups, we now encounter alcohols. Alcohols are molecules that contain an OH group or hydroxyl group instead of a hydrogen. Okay, so a very common example of an alcohol is ethyl alcohol or ethanol. Primary, secondary, and tertiary apply to alcohols just like they apply to alkyl halides. So ethanol, for example, is a primary alcohol. Another way to think of alcohols is from the perspective of the oxygen. And in this case, they're an oxygen bound to one organic group and one hydrogen. If we increase the complexity slightly further, we run into ethers. And this is where you have an oxygen that is bound to two organic groups. We abbreviate this ROR. Okay, a couple of examples of ethers that you may have heard of. The molecule on the left is called diethyl ether. It gained fame because it was actually the first anesthetic the first molecule ever demonstrated to have anesthetic properties back in 1848 at Massachusetts General Hospital. Another molecule you might have heard of is methylterbutyl ether, which is shortened to MTBE. And this used to be used as an additive for gasolines to make them burn cleaner. Unfortunately, MTBE has some small amount of water solubility and was getting out of pipelines and causing environmental problems. An important subclass of ethers that you have to be able to remember are called epoxides. Now, epoxides are cyclic ethers, but they are a very special subset of cyclic ethers in that they contain a three-membered ring. We will get back to epoxides at the very end of this semester and talk a little bit about their chemistry. Finally, the last of the simple functional groups are the amines, and those are functional groups that contain a nitrogen atom. Okay? Amines can also be classified as primary, secondary, or tertiary, but the rules are a little different for amines than they are for alcohols or alkyl halides. In this case, we classify molecules as primary, secondary, or tertiary, depending on how many organic groups are bound directly to the nitrogen. Okay, let's look at this. A primary amine has one organic group and thus two hydrogens bound to the nitrogen. A secondary amine has two organic groups and only one hydrogen bound to the nitrogen. And a tertiary amine has three organic groups and no hydrogens bound to the nitrogen.